Welcome to air conditioning. Um, this is going to be done in parts. So this is the first part of the air conditioning system. Okay, and we're going to take a look at different types of heat. Some of you have already started your modules on Electube, so you've run into that. So we're going to get going on this. It's not quite air conditioning weather yet. Um, we haven't had a 80-degree day yet, so air conditioning isn't in demand yet. But once hot weather gets here, a lot of people are going to want their air conditioning fixed. So it doesn't make any difference what type of vehicle or trucks or even excavators, heavy equipment now have air conditioning on it. All the systems work very similar. So if you can understand the air conditioning system in a passenger car, it's pretty much the same on most of the vehicles that you would be dealing with other than the hybrid vehicles, and that's how the compressor is controlled with an electric motor. So here we are in our very fine, you can see it's a Ford product, and your book that you're using for the textbook is from Ford. It's not outdated other than the refrigerant system that's used. I should say the refrigerant. The refrigerant in that book is R12 and 134A, and R12's been discontinued. 134A is still in use, but there's going to be a new refrigerant that's coming out, or that's being used right now, and that's R1234YF. So in this slide, they're just showing different ways that the vehicle could be heated or cooled by the elements. So just because of that, we need a good heating system as well as a good air conditioning system to keep us comfortable. So this is the way our body can give up heat. We operate at about 98.6 degrees Fahrenheit. So usually we're a little warmer than the ambient air temperature around us. So convection, that's a process where our body heats the air up and the air starts circulating around us from the ground up. Usually at the ground level, the air is a little cooler, and so you can get a convection process started. Radiation, we radiate heat off our body, so that's going to be given up to the cooler air around us. And then evaporation, when we perspire, the drier the air is, the quicker our perspiration will evaporate, and that helps cool us off. We all know what it's like to be in a real humid day and how uncomfortable that can be. So this is just showing that convection. The heat starts moving around us, and we like to be comfortable. So most of our relative humidity, we'd like to be around 45%, 50% relative humidity. Drier than that, we might be a little uncomfortable, but higher than that, we definitely start getting very uncomfortable. We've all experienced a very high humid day in the summertime, and just because of that, we're very uncomfortable. So one thing the air conditioning system does is dry the air out, or dehumidify it, make it drier, so we're more comfortable, as well as cooling the air. So again, conditions affecting the body comfort, temperature, relative humidity, and air motion. So, our comfort zone is somewhere right around, 70 to 80 degrees Fahrenheit with a humidity of approximately 45 to 50%. So the cooler it is around us, the greater the temperature differences around us, the faster we can get rid of heat. So if it's a 60-degree day, I'm going to cool off much quicker than if it's an 80-degree day, just because of the temperature difference of my body temperature and to the ambient air temperature around me. So, if it's warmer than 98, then my body can't give up heat, okay? And if it's like 104 out, then actually where I'm cooler, heat would be transferred into my body, okay, or into our bodies, and just because of that, we would, start to overheat, so to speak. So, temperature, relative humidity, air motion, just having a breeze blowing around us or having a fan on us helps cool us off. It helps with the evaporation process. So just because of that, just having some air motion can make us feel more comfortable. So principles of heat transfer, some of the things that we look at, heat is the energy that causes an atom to be in motion. Temperature basically is the measurement of the atom's movements. And sensible heat is heat that causes matter to change temperature. Then we have what's referred to as specific heat capacity, and that's the heat needed to change the substance, the temperature of a substance. And BTUs is what we use in the standard unit for the measurement of heat capacity. So, 1 BTU would raise the temperature of 1 pound of water 1 degree. And then we have latent heat. And latent heat is heat that causes matter to change states without a change in temperature. And sometimes this is referred to as hidden heat. So, we've heard like the phrase that water feels as cold as ice. Well, water can be frozen at 32 degrees or it can be liquid at 32 degrees. It depends how much latent heat is in the water or ice, whether or not it's ice or if it's just water. So this is showing the specific heat capacity of water, okay? So this is 1 BTU. So 1 BTU would raise the temperature of 1 pound of water 1 degree Fahrenheit. So we can use BTUs as a temperature measurement too. So heat, something that is warmer is going to move to a cooler area. So heat that's trapped in this pan of water, that's what this represents, is going to travel to the cooler air around it. So the heat's going to be pulled out of the water. So until the water equalizes in temperature, heat's going to continue to move from the water to the cooler air around it. And this shows, this is a graph. There's 2 in your textbook. This is out of a different textbook, but it follows the same pattern because we're looking at water, okay? Or water can be in 3 states, a solid being ice, liquid or steam, which is a vapor. It's a good one to relate to refrigerant. So on this, if we look at the graph on the left-hand side, we are going to see at 32 degrees, that's where water can be frozen. So we started off at 0.1, basically at 0 degrees Fahrenheit. We're going to raise the temperature up to 32 degrees. So that's going to be a 32 degree change from 0 to 16. So we get up to 32 degrees, and we have this ice is still frozen, okay? And now to get it to change over to a liquid, we need to add heat to it. And while we're adding heat to it, the ice is going to start to melt, okay? And once that pound of water has absorbed 144 BTUs of latent heat. In other words, there's not a temperature change taking place between 0.2 and 3 on this graph. So until we get here, once we get 144 BTUs in there, now we have all liquid, okay? So once we have all liquid, any heat added after that will make a sensible heat change. So as we continue to add heat after 0.3, now we're going to have an increase in heat or temperature, okay, as we add more heat content to this pound of water. Once we get up to 212, which is the boiling point of water, once we get up to 0.4, now we will have the water will start to boil, and now we have to add a lot more latent heat to get this 1 pound of water to change over to steam. So from 0.4 to 0.5, it's going to take 970 BTUs of latent heat to get 1 pound of water to change completely over to steam. So during this latent heat, additional latent heat being added in, the water is going to start to boil at 0.4. And as we get over to 0.5, once we get to 0.5 with 970 BTUs of latent heat, now we have all steam at 0.5. So it took 970 BTUs of latent heat or heat energy added to that pound of water to get it to change completely to 1 pound of steam, and that's at 0.5. Now, if we add more heat to this, now we're going to have a sensible heat change. So now we're going to have an increase in temperature. So once we raise the temperature above 212 degrees Fahrenheit, that is considered superheated. So now we have vapor that has increased its temperature, so now it's considered superheated. And this is the latent heat of vaporization. So where we've changed the state of H2O, or water, we could freeze it in 1 pound of ice. If we thawed, then we'd have a pound of liquid. And if we heat it and change it to a vapor, we would still have a pound of steam. So we can change its state without changing its mass. Okay, so the change of state does not change the mass of the water. So here's the graph of latent heat of condensation. So this is just the reverse of vaporization that we looked at in the other graph. So if we have that steam and it's heated above 212, we have to get it cooled down. So we're going to have a sensible heat change from up here to this point, okay? So once we get it down to 212 degrees, Now we're going to remove heat out of the steam, and it's going to start to condensate. And it's going to condensate completely into water once we remove 970 BTUs out of the steam. At that point, we will have all liquid, okay? And if we cool it a little more, okay, we're going to start seeing a sensible heat change. In other words, temperature is dropping. And once we get below 212 degrees, with 970 BTUs taken out of the steam, we will be all at liquid. Once we start dropping the temperature, this is what they refer to as subcooling. It's no longer a vapor. That pound of steam has condensed completely into 1 pound of water if we have a sensible heat change below 212 degrees Fahrenheit. So this is where we get into subcooling. We're going to cool that off until we get down to 32 degrees Fahrenheit. At that point, we'd have to remove 144 BTUs of latent heat. And once we get to this point, we would have our pound of ice again. And then we can cool it even further and make that solid colder. But this is the latent heat of condensation. So when we change the state of a vapor completely into a liquid, that's when we have the biggest heat transfer taking place. And vice versa, when we go from a liquid to steam, that's also where we have the biggest transfer of heat taking place in both of those events. Now, both of these graphs of latent heat of condensation or latent heat of vaporization is taking place at sea level. And that's the temperature and pressure that we'd be working at. So up here is just showing that we are looking at atmospheric pressure of 14.7 psi. So just like in the cooling system on a vehicle, if we have all water and we don't pressurize the cooling system in the vehicle, water boils at 212 degrees Fahrenheit. So if we had an open cooling system and water got up to 212, it's going to boil and evaporate. So if we pressurize the coolant, being straight water, and we put 16 pounds of pressure on that system, now we're going to raise the boiling point of water to 260 degrees Fahrenheit. So just by pressurizing the liquid, we can prevent it from boiling. So we're going to do the same thing with the refrigeration system. The refrigeration system is a sealed system, okay? The only way we can add refrigerant to it is to open the system up when we service it and put more refrigerant in. But it's sealed, and where it's sealed, it's going to have pressure in that system at all times. So this is showing a graph of the boiling and condensation point of R12, 134A, and R1234YF is very, very similar. They have very similar properties. So we're just going to run with this graph because it's in your textbook. So the line represents the points that the refrigerant could boil at due to the pressure. So on this side, everything is going to be a vapor. Anything on this side of the line is going to be a vapor. Okay, so this is the vapor side. Anything on the other side of the line is going to be liquid. So this is showing on this side, we're going to have vapor. On the other side, we're going to have liquid. And it's just because of the temperature and pressure on the refrigerant in the sealed system. So in a refrigeration system, there is going to be liquid and vapor. Okay, we're going to use a compressor to actually increase the pressure on one side so that we can get the vapor to condensate. And then on the other side of the system, or the low pressure side, we're going to lower pressure so that we can get it to evaporate. So again, if we increase the pressure on a vapor, it's going to heat up. And we do this is just a compressor. This is not like a combustion chamber or a piston, and we're going to have an explosion take place. This is basically a pump that is going to move the vapor through the refrigeration system. So we're on the left-hand side, you can see we're drawing in a cool vapor, and on the other side we force the vapor out, and because of that we had a pressure increase, and so over here this is going to get hot. This is cool. This is on the inlet side. Okay, so temperature is going to increase with pressure. We can't compress a liquid. If we did, we'd damage the compressor. Okay, we've had coolant leaks in the cooling system in a vehicle where antifreeze gets into a cylinder and the engine tries to crank over and it'll actually hydrostatically lock up. You can't compress that coolant. If it does compress it, something's got to give. We've found bent connecting rods in a vehicle because of liquid coolant getting into the combustion chamber and the engine trying to compress it. So let's take a look at the refrigeration circuit. So here we're looking at the refrigeration circuit, and we're looking at the main components of a TXV system, or a thermostatic expansion valve. Some manufacturers may refer to this as a variable orifice tube. So we have the compressor. That's going to be belt driven by the engine. We have the condenser. That's going to be the heat exchanger in front of the radiator. With a expansion valve system, you're going to have a receiver dryer. From the receiver dryer, we have a liquid line going up to the expansion valve. And after the expansion valve, we have the evaporator. That's going to be in the air distribution box along with the heater core. And then we would have the suction line leaving the evaporator going back to the compressor. And sometimes they will refer to it as a frost line just because it can frost up. So those are the major components: compressor, condenser, the receiver dryer, the expansion valve, and the evaporator. And then of course we'd have the lines that are connecting those components together. Now the AC system, nothing will exchange heat unless the compressor is engaged. So the compressor would be engaged with the AC being requested on. Compressor be spinning, moving the pistons back and forth, and that's going to start the refrigerant to flow. So the refrigerant flowing to the condenser is going to be a high temperature, high pressure vapor. Okay, the compressor can't operate on liquid refrigerant, so just because of that, it's going to be vapor coming into it and vapor leaving it. So the vapor goes into the condenser. We have airflow across the condenser where it's in front of the radiator, either by the vehicle moving or by a fan pulling air through the radiator if it's sitting still. And inside the condenser, the refrigerant's going to condense into a liquid. It's still going to be high temperature, but it's going to be a liquid. So from there, the refrigerant flows into the receiver dryer. From the receiver dryer, it's going to flow as a liquid up to the expansion valve. There, on the other side of the expansion valve, we can see things are shown in blue. That's low pressure. Okay, so the refrigerant goes through the expansion valve, and on the other side it's low pressure. It goes in as a liquid. So we have liquid, low pressure refrigerant going into the evaporator. The evaporator is going to have airflow across that due to the heater fan. So the fan's pulling ambient air into the evaporator, and because of the temperature change and pressure change, the refrigerant is going to change its state from a low temperature liquid. It's going to start to vaporize into a vapor, low temperature, and it's going to completely vaporize inside the evaporator core and move as a vapor to the compressor as a low temperature vapor. And that'd be the refrigeration circuit for a TXV system. So we're just taking that diagram on the other side, and it's flipped over a little bit. But here we're showing the high pressure side and the low pressure side. So we're just taking a dividing line to show the high pressure side, which is on the upper side this time. Refrigerant is flowing into the condenser, high temperature, high pressure vapor inside the condenser. It's going to condense into a liquid. It's going to leave there as high pressure, high temperature. There's about an 11 degree temp change from the inlet to the outlet on the condenser. So there is a temperature change that takes place, but you know, it's still considered high temperature liquid that's leaving the condenser. From there, it goes to the receiver dryer. Receiver dryer would be vertical instead of horizontal. And this is just to illustrate it in the diagram. So we'd have that liquid, high temperature refrigerant going into the receiver dryer, and from there, the liquid refrigerant, high temperature, high pressure, gets to the thermostatic expansion valve. On the low pressure side, the liquid refrigerant goes in. It starts to get into the evaporator. The evaporator has warmer ambient air flowing across it, so the refrigerant wants to vaporize, and it's going to start to absorb the heat out of the air. And it's going to heat up and change its state from liquid, low temperature, low pressure refrigerant to vapor that's low temperature, low pressure, and flows back to the compressor. And you can see they're showing that it could be referred to as a suction. And it's just the low side sometimes is referred to as the suction side, pulling the liquid, the vapor back to the compressor. So this is just showing another layout of the expansion valve. The expansion valve shown in this one is more of a H valve configuration, or they may refer to it as a TXV block valve. And it makes a very convenient connection point for the evaporator connection to the high side and low side lines. So again, they refer to this as an H valve. In most manufacturers, that's what they're using now instead of a capillary tube TXV system. So again, you can see the compressor is running. If the compressor is the drive plate right here is turning, then we're moving the refrigerant through the system. It's being pressurized, so that refrigerant is moving as a high temperature, high pressure vapor into the condenser, airflow across it. The condenser is going to be hotter than the ambient air. So the refrigerant is going to give up its heat to the surrounding air and condense into a liquid. So from there, the high pressure liquid is flowing into a receiver dryer. It leaves the receiver dryer as a liquid. And then we get to the TXV valve. So right here, we have high pressure on this side coming up to there. Right after that is low pressure liquid going into the evaporator. With the air flowing through the evaporator core, the liquid refrigerant is going to start to vaporize. It wants to change into a vapor because the low pressure and the high temperature around it. So it's going to vaporize and it's going to leave there and go back out through this section of the expansion valve. And this is pretty much a straight shot through, and it leaves the evaporator as a vapor, and it travels back to the compressor as a low temperature, low pressure vapor. So this is an orifice tube system. The restriction that separates the high side to the low side is an orifice tube instead of a TXV valve, thermostatic expansion valve. So because of it's an orifice tube system and it's fixed, so this is non-adjustable. So because of that, the amount of refrigerant that is in the system has to be very specific for the system to work correctly. So other than the restriction, the only other change that we make in the system would be the component that's referred to as an accumulator. And sometimes they refer to it as a suction accumulator because it's on the suction side or the low pressure side. You can see we have the high pressure side, low pressure side. We've got that dividing line again that's being shown. So again, everything on the upper part is high pressure, high temperature. As it leaves the compressor, it's going to be all vapor. Same process, it goes through the condenser. The refrigerant is going to give up its heat, condense into a high temperature liquid, and from there it flows to the orifice tube as a liquid. So everything on the high side would be hot. So when we get to the orifice tube, now refrigerant is flowing through the orifice tube, and it's flowing through there as a liquid, and it goes into the evaporator core as a low temperature, low pressure liquid. and inside the evaporator it's going to start to vaporize. So it's going to start absorbing heat from the air that's flowing through it. And it's going to leave the evaporator as liquid. As vapor. So that vapor is going into the accumulator. The accumulator sits between the evaporator core and the compressor. It's in the suction line. And from there, the vapor is going to go into the accumulator. And this would be vertical, as shown horizontal. So the gas would come in here and then would leave through this part, going back to the compressor as all vapor. So the purpose of the accumulator is if any liquid refrigerant came out of the evaporator because of low temperature, again, the orifice tube can't be adjusted in a fixed orifice tube system. So where it's not adjustable, there is a chance under certain atmospheric conditions, temperatures, that the refrigerant may not all vaporize. So it's going to go into any liquid that gets out of the evaporator is going to go into the accumulator, and the accumulator would allow that refrigerant to expand one more time and change over into a vapor before it moves on to the compressor. The compressor does not like liquid refrigerant. It can damage the reed valve system that the compressor uses. So because of that, we will have an accumulator. If you have a fixed orifice tube, you will have the accumulator, and it's going to be located after the evaporator, but before you get to the compressor. So refrigeration components, we'll start with the refrigerants because there's 4 refrigerants that have been used or are being used. So CFC 12 is no longer being produced. Okay, this was the first refrigerant manufacturers used for the refrigeration systems in automobiles. So, as non-flammable, non-toxic, pretty safe. The biggest problem that refrigerant 12 has is the fact that it's ozone depleting, and it has a extremely high global warming potential, and it's 10,900 times greater than CO2. CO2 is what we use as the benchmark for global warming, and CO2 has the global warming potential of 1. So CFC 12, R12, sometimes you've heard of it as referred to as Freon, okay, and it has a boiling point. In other words, it wants to be a vapor at minus 22 degrees Fahrenheit. So refrigerants want to be a vapor. They do not want to be a liquid. They want to vaporize. Where we have them in a sealed container or a sealed refrigeration system, they can't change all into vapor. So we're going to have some vapor and liquid in the refrigeration system. HFC 134A or R134A. It has a low boiling point also of minus 15 degrees Fahrenheit. It's in use today. Manufacturers are still using this. This was the replacement refrigerant for R12. R12 systems could be retrofitted and you could use 134A in those systems. Again, low boiling point, minus 15 degrees Fahrenheit. The problem with HFC 134A is it's a global warming gas and is 1,430 times greater than CO2 as a greenhouse gas. So on the 1430 number, I found some different numbers. The 1430 seems to come from the California Research Board and the EPA. So this is the number that they're using to show how many times greater it is as a greenhouse gas. So this is being used today in a lot of vehicles, but it's being changed over to the next refrigerant we're going to take a look at. So this is the new refrigerant that's being used. This is R1234YF, okay, and it's being phased in. Not all manufacturers have started using this, but quite a few vehicles have it now. And the big selling point here is two things. One, it's only 4 times greater than a CO2 gas as a greenhouse gas. So it's only 4 times greater than CO2. So with the low greenhouse gas effect, and along with that, the other thing is it has a lower boiling point than R134A. So because of that, it would have a little better performance than 134A does as a refrigerant. The other refrigerant that's being looked at very closely by the European group is using just CO2. Now, CO2 is a gas, so it has a very low boiling point of minus 70.6 degrees Fahrenheit. It wants to be a gas. So just because of that, the greenhouse gas effect is 1. That's our standard. But the operating pressure for a refrigeration system using CO2 is 5 to 10 times the pressure of 134A or 1234YF. So because of that, the components that would be used in a R744 system would have to be much stronger to withstand the pressures that are being used in that refrigeration system. At this point, no domestic manufacturers are using CO2 as a refrigerant yet. Now, compressors, there's a variety of compressors out there. As you go through your Electube modules, they're going to highlight some of those. What's being shown here on the left-hand side is the early model. This was a 2-piston compressor that was used in early production. The one on the left is a modern design. This could either be designed as a scroll compressor or a variable displacement wobble plate compressor or a piston compressor. They're all very similar. What's being shown on the front, this is the pulley and clutch assembly. The pulley is being driven by the serpentine belt. And then we actually have a magnetic clutch that's behind the compressor pulley that's going to pull in the drive plate. And the drive plate's got these spring plates here. So this component here has to spin. When we turn the AC on, if this part here is not spinning, the belt's always going to be driving the pulley. But if this doesn't pull in and engage and spin at the same speed as the pulley, then the compressor did not engage, and it could be an electrical fault why the compressor didn't engage, or it could be that the refrigeration system is low enough on refrigerant that there's not enough pressure to get the switches to close to engage the compressor, and they do that as a fail-safe. Refrigeration oil has to circulate with the refrigerant to lubricate the compressor components. So this is showing a cutaway of a compressor, and this is the early style. But as the piston pulls down, refrigerant vapor is going to be pulled into the cylinder. And you can see there's a little reed valve that just pops down. So that opens and allows the refrigerant to be pulled into the chamber. The reed valve up here is closed. So that would be like the intake stroke, and then when we push the refrigerant out, this reed valve closes and this one pops open and allows the refrigerant to flow through. So the refrigerant's not being compressed inside the chamber. The refrigerant is being moved to the high side, and the pressure is being created by the restriction in the line to the evaporator. So that's where the pressure is being built. It's not being built inside the compressor. It's because of the restriction. The compressor is just moving the vapor. So the condenser is where we're going to get the refrigerant, high temperature vapor to cool off and condense into a liquid. So this is a series design condenser. In other words, the refrigerant has to flow in series right through the tubes, coming in at the top as a vapor, and when it leaves, it's coming out of the bottom as a liquid. And again, there's cooling fins that surround this. The more surface area the condenser has, the greater capacity it is to give up heat. So the cooling fins, most of these are made out of aluminum. The cooling fins have to allow air to flow through it. And some of the problems that we have with condensers where they're right in front of the vehicle radiator is that they collect a lot of debris. So sometimes the cooling fins will get clogged up with fine dirt, road debris, paper bags, plastic bags could get in front of the condenser. That's going to affect the airflow across the cooling fins, and that's going to affect how effectively the condenser actually works. It requires a lot of airflow through the condenser to get that refrigerant to change its state from a high temperature vapor into a high temperature liquid. So that's the purpose of the condenser. Now, the condenser could be mounted to the radiator through some mounts, or it could sit on its own rubber mounts in front of the radiator. So sometimes you might have to remove both to get the condenser out of the vehicle. Condensers, I've always said the condenser is usually the first thing that in a frontal crash that gets injured in the refrigeration system. Now the cooling fins, if they get bent over, they can be combed out. So if these get laid over so it's blocking air, they make a comb that's made out of plastic that has so many fins per inch, and there's like 5 or 6 of them on the comb, so you can match this the cooling fins out, and then you just rake through those and get them to stand back up straight again so the air can flow through there properly. And I've had some refrigeration systems that seem to not work properly, and you flush the condenser out with water from the back side just to blow the dirt out of it, or use compressed air to get the dirt out of it, and it will help get the condenser working properly again and the AC system. If we can't give up the heat in the condenser, then we can't extract the heat out of the interior of the vehicle and the evaporator. So the condenser has to work as well as the evaporator to have the AC system to work properly. So this is the evaporator. This is the other heat exchanger. This is the one where the liquid refrigerant's coming into it, and liquid refrigerant usually flows into the bottom. So they're showing the inlet here at the bottom. So this liquid refrigerant would flow in after the orifice tube or TXV valve, depending upon which system you have. And so we'd have the low temperature, low pressure liquid refrigerant coming into the evaporator core. And warm air is flowing through this, and because of that, it's going to get the temperature change take place that the liquid refrigerant needs, so it will vaporize all into a vapor and leave the evaporator core out the outlet as vapor. So this is where the liquid refrigerant vaporizes, low temperature liquid, low pressure, and it changes into a low temperature, low pressure vapor. Here's a picture of a evaporator core out of the vehicle. This came out of a Ford Ranger, I believe. And so it gives you an idea of what an evaporator core would look like. The black component hooked to it is the accumulators. That would be between the outlet line, which is right at the top. This is the outlet. This is the inlet right here. So the liquid refrigerant's flowing in. At the bottom, low temperature, low pressure refrigerant, and it flows in and across the bottom. And then about halfway up is vaporizing, so it starts to vaporize in the middle, and it's going to exit out the top as vapor. Now, if any liquid does come out of the evaporator core, it's going to get trapped in the accumulator, which is being shown here. So the liquid refrigerant would drop to the bottom. And this would be the outlet right here going back to the compressor. This is being shown there. So this is just a picture of the evaporator core. And the evaporator cores would look are identical basically for a TXV system or a orifice tube system. The only difference would be the connection that would be used in this area here for a TXV system. So this is one of the restrictions that would separate the high and low side. So this is a fixed orifice tube being shown here, and basically the inside diameter that's being shown here is the orifice itself. The entire tube basically is the housing for it, which has a fine mesh screen to prevent any debris from plugging up the orifice tube. And usually any debris that's in the refrigeration systems, usually from the manufacturing process, so they put a little screen there to help make sure that anything that broke free inside the system is not going to get into the actual orifice. It does have a direction to flow, so refrigerant's coming in on this end where we have the most screening, and that's so that it won't plug up, and then we have the vapor go through the orifice, and on this side, the liquid is going to be on this side, and liquid low pressure, low temperature liquid is coming out on that side. 2 O-rings are on this one. That's to seal it inside the tube that it would reside in to make a good seal, so it forces all the refrigerant to go through that small orifice. And this one's being shown, the inside diameter of that is 0.067 thousandths of an inch. So size of a spark plug gap on some manufacturers' spark plugs. Okay, so it's a pretty small hole that refrigerant is flowing through as a liquid. This is just a picture of the orifice tube, give you an idea how large it is. So, and all of these seem to be a standard length. This one here is shown about 3.5 inches long, and this does show you the fine mesh screening to protect the orifice tube. Direction of flow is going to be this way. Okay, this one only has 1 O-ring on it, so it just depends on the manufacturer which how many O-rings they're going to use on that. And here you can see the little orifice that's there, and you can see like a little bit of the orifice here where it would allow the gas to come out. I mean the liquid come out on this side, okay? And you can see there's some little tabs back here, and this is so that you can actually pull this out. The O-ring will stick, and if you had to change it, the only reason you'd have to change an orifice tube is if it got plugged up by debris, which means this whole area would be packed and restricted. So if it's packed and restricted with debris, the only place it could come from is usually the compressor. So because of that, we would be looking at a compressor failure if this was packed with debris. But that's an orifice tube. Now the orifice tube on a lot of vehicles is going to be very close to the evaporator core. So this is that inlet tube to the evaporator core that I showed in the previous slide, and you can see this is the accumulator right here. So that's the accumulator. The orifice tube is actually going to sit in here. And something to look for to see the location of an orifice tube is looking for a crimp somewhere right after a connection or right before a connection. So you can see right here we have some crimping. That's so the orifice tube can't slide beyond that point. So it's designed so it would be held right in this tube. So the orifice tube would slide in this direction. This would be direction of flow. So the orifice tube is going to go in to that evaporator core just like that. This is just showing the orifice tube being installed. We'd put a little refrigerant oil on the O-ring so it would slide in there properly, and we'd push it in so it would be flush with the end of this fitting. So we would push it in to this point. That way we can grab the tabs either with a tool or grab this piece right here with a pair of needle nose pliers to pull it out. So if we are using an orifice tube system, we will have an accumulator also. Those are what we would see different in the refrigeration system from a TXV system. Okay, we would look for an accumulator. So this is the layout of an accumulator, and from the evaporator we would have vapor coming into the accumulator at the top, and again, if any liquid refrigerant, low pressure, low temperature liquid refrigerant made it to the accumulator, it gives it a chance to basically drop to the bottom, So you could end up with a little liquid down here, and then it would vaporize. The accumulators are large, so just because of that, it'd give plenty of room for the liquid to vaporize before it left and moved on to the compressor. So the gas would move up and then come down through and out to the compressor. Inside the accumulator would be a desiccant bag, okay, and that's this component here as shown. And that desiccant bag is to absorb any moisture that may have got into the refrigeration system. We don't want air and moisture in the refrigeration system. So in the service procedures, which we'll be getting into in part 2, we would actually pull all the air out of the refrigeration system, put it under a vacuum before we introduce the refrigerant into the system. So this is the accumulator. And at the very bottom of this, there's a little strainer, and that's to make sure if any oil that was going to get trapped there, if there's any debris in it, it would be strained or caught by the strainer. So oil, a little bit of refrigeration oil would move through this accumulator, and refrigeration oil might collect in the bottom. So as the refrigerant moves through, any oil is going to be picked up by the refrigerant and actually goes on to the compressor to lubricate the compressor. But an accumulator is used with the orifice tube system. So here's a thermostatic expansion valve with the capillary tube that was on the other slide. So again, we would have liquid refrigerant, high temperature, high pressure coming in on this side of the valve, and low pressure, low temperature liquid on the outlet side. So this area here on the TXV valve, they refer to it again as an orifice, but because of the way the pin can move up and down in this system, they consider it a thermostatic expansion valve instead of an orifice. Some manufacturers will refer to this as a variable orifice system. So they show the diaphragm, and on the upper side of the diaphragm, that would be filled with liquid refrigerant, and that liquid refrigerant goes all the way to the remote bulb, and the remote bulb is hooked to the outlet tube of the evaporator core. Now, some of these, it's kind of hard to see with the capillary tube system because they can actually put the thermostatic expansion valve in the interior of the vehicle very close to the evaporator core. So it just depends on the manufacturer where this is going to be located, but it has to be located very close to the evaporator core on the inlet side or on the inlet side of the evaporator. So as the refrigerant on the outlet changes its temperature, the orifice can change up and down to increase the refrigerant flow into the evaporator or decrease the refrigerant flow into the evaporator to make sure that all the refrigerant is going to vaporize when it leaves the evaporator core so that it can get back to the compressor as a low temperature, low pressure vapor. This is just showing the expansion valve being moved due to the temperature inside the capillary tube sensing bulb. Okay, so open, the pressure is high enough. Now we're going to move this down off the seat. They refer to this as a pin on some of these. And it's going to move the ball down off the seat so that the liquid refrigerant can flow through. And in this one here, the temperature is cooler. So just because it's cooler, we're going to close this up so less refrigerant can get into the evaporator core. And that, again, to make sure the refrigerant all vaporizes before it leaves the evaporator and moves on to the compressor. The spring that's being shown right here, they refer to this as a superheat spring. The spring sets up the temperature change that's going to take place between the sensing bulb and the spring to allow how much superheat we're going to allow that refrigerant to increase in temperature. Now, superheat is the sensible heat absorbed by the refrigerant after it's vaporized and passes through the evaporator. So this would be a sensible heat change of the refrigerant. So it's changed its state, and now it's picked up enough heat that it's changed its temperature and it's warmed up a little bit. So because of that, it would be superheated. And it's just the temperature difference of the refrigerant between the inlet and outlet of the evaporator. That's the superheat. And if the vapor or refrigerant is superheated, so the vapor would be superheated, it has to be all vapor. It can't be any liquid if it's had a temperature increase. So that temperature increase could be from 4 to 16 degrees Fahrenheit, depends on the manufacturer, how much superheat they wanted to have take place in that low pressure, low temperature evaporator side of the refrigeration system. And again, this is to ensure the refrigerant has completely vaporized before leaving the evaporator. And those expansion springs are calibrated for that difference on the inlet and outlet side. Excuse me. The expansion valves would be changed by part number, so we would be ensuring ourselves we had the proper spring in there by the part number change if we had a problem. So this is showing the TXV valve block style valve, and this has become very, very popular because it makes a very easy connection for the high and low side lines going to the evaporator. So at the bottom side, bottom portion, this would be the high pressure side coming into the valve, and you can see in the back is the metering orifice, and then this is the connection up here for just the evaporator outlet, which would be low pressure, low temperature vapor flowing right across this little section here. This is basically the sensing bulb that's hooked to the diaphragm at the top that's going to make the change down here at the metering valve right at the bottom. So this is what we'd be looking at for a H-style expansion valve. So these are very popular because it allows a very easy connection for the high side line and the low side line for the refrigeration system. So this is a picture with the rule so that you get an idea how big the H-valve block would be. And these are made out of aluminum. So this would be where the connections are going to be made. Basically, there's a bolt system that would hold the lines up against this with O-ring seals. And you can see this would be the high pressure side coming in, and then on the other side it'd be low pressure liquid, and this is the low pressure side coming back to the compressor. And again, this is the sensing tube in here, and this is the little adjustable pin down here at the bottom. So this is an H style TXV valve, H block style. So if you have a TXV system, you will have a receiver dryer. So the receiver dryer sits in between the condenser line to the TXV valve. So this is the receiver dryer. And since the TXV valve works best with liquid refrigerant, this is going to be the low catch basin on the high pressure side, high temperature side, to catch any vapor that may have come out of the condenser, so that all liquid would get to the TXV valve. So on the inlet side from the condenser, we would have high temperature, high pressure liquid coming in, and if there was any vapor, high temperature, high pressure, it would get trapped at the top here. So that vapor would actually rise to the top. The liquid refrigerant would flow through. There are some filter pads here, and that's to catch any debris that may have come from the manufacturing process, or and that's about the only time anything would get in there, unless we're having a compressor failure, which means we could find like little Teflon rings off of the compressor piston getting trapped in here. Okay, that's so we don't plug up the TXV valve. So, you know, we have the liquid refrigerant going through the filter pads. This also contains desiccant to pick up any moisture. So that's what the desiccant's there for. And so that would pick up any moisture that was in the system. And then the liquid refrigerant would accumulate and be moved on to the TXV valve. Now, some receiver dryers now are being incorporated into the outlet end of the condenser. So you might not find one of these as a standalone component. It can be incorporated into the condenser now, so that it's more compact, so they can get more under the hood of the vehicle. Well, that brings us to the end of part one. So hopefully this was informative, and hopefully the pictures definitely helped explain the refrigeration circuit. So part two, we'll get into more of the diagnosis and service of the components.